Hello and welcome to this AQA Further Math Statistics video, the third in the series looking at continuous random variables, this time looking at confidence intervals, and in this first video looking at samples from populations. So first of all, a reminder here of two terms that you should be familiar with, parameter and statistic, and just make sure you're clear in your own mind about the definitions of those. A parameter is a measure summarizing an attribute of a population. So if we think about averages, probably you're familiar with mu being used to describe a population mean. And with statistic, we're looking at a measure that summarizes an attribute of a sample. And again, if we look at average, you're probably used to seeing X bar and using X bar to indicate a sample mean, a statistic, a measure that summarizes an attribute of your sample. Now, what do we mean by sampling from a population? So there's a little illustration here just to indicate to you what we're talking about here. So we have here our population made up of lots of members xi. And what we're going to be doing is taking several of these items in these samples here. So we have lots of different samples that we've taken, and we are going to be looking at the data that we've got in the sample and things that we can work out from our samples. And each sample will comprise n items from our population. And that means that our sample has sample size n. So you can imagine we have n different selections from our population in each of those samples. And for the purposes of what we're doing here, we will always assume that these samples have been selected at random from our population. So if we now move on to looking at our samples, and if you imagine for each of our samples here, and I have just imagined we have k samples, we could have 10, we could have 100, we're taking out, remember, n of the population items each time to be within our samples, and for each sample, imagine that we work out the sample mean x bar. So we have k lots of x bar, so for each sample we have worked out the sample mean. For our population here we have the population mean indicated mu and the variance indicated sigma squared. So we know the mean and variance for our population. What about the mean and variance? What about the distribution of these sample means here? Well, that's what we call the distribution of the sample means. Now, looking at a specific example, if we imagine our original population is normally distributed with mean mu and variance sigma squared, and imagine we take n lots of members of our original population to be in our samples over here, and we work out the means of those samples. Actually, the sample means also follow a normal distribution, and the mean, I think intuitively, would be the same as the population mean. If we took out absolutely every sample we could do and worked out the average of the averages, that would indeed give us mu. However, the variance is reduced by a factor of n for our sample means, and again this does make sense because in our original population we may have a very small value and we may have a very large value, and we could get the very smallest and the very largest in our samples, but of course these values that we're looking at in terms of their distribution, these are sample means, and therefore they're going to not be the smallest or the largest value that you would get in the original population. They're going to gravitate towards the value of mu, their averages. Therefore, it's expected that their variability is going to be reduced when you compare it to the variability of the original population. And you can see this summarized over here, and you do have this information in your formula book. We'll look at it a bit more in later videos in this series. So if we have the mean of x is mu and the variance of x is sigma squared, the mean of x bar, those sample means, the average of the sample means is mu, and the variance of the sample means is sigma squared over n, or the standard deviation is sigma over root n. It's reduced by a factor of root n, and sometimes this is called standard error. So there's an illustration here that's quite nice to look at. Here I've generated a population, quite a large number of data points from a normal distribution with mean 50 and standard deviation 18.4. And you can see that bell-shaped curve coming out because this population is normally distributed. If I then look at taking out samples of size 16 from that population, and I've done that quite a few times as well, you can see that it's still a normal distribution, and in fact it's still centered around 50. The mean comes to 50, but you'll notice that the standard deviation is now reduced by a factor of root 16, or 4. So our original standard deviation was 18.4. Our standard deviation now is 18.4 divided by 4, 4.6. And clearly this distribution is sort of shrunk. It's nowhere near as spread out as our original distribution was. And we're now going to look at a really important theorem in statistics. You may like to read this up in your A-level textbook or perhaps other textbooks. You don't need to know any proofs for this, you just need to know the result. And this is going to be very important in working out confidence intervals and doing more hypothesis tests that you're going to meet further on in your A-level maths course. So here we've gone back to our original population with mean and variance, mu and sigma squared. We don't know the distribution of this population, could be anything. We've taken out k samples, each of size n, and we've worked out the sample mean for each of those samples. And the central limit theorem tells us that our sample means will follow a normal distribution, again with mean the same as the original population mean, but variance, population variance divided by n, regardless of the distribution of the original population. So we may have no idea what distribution this population has, but as long as our sample size is greater than or equal to 30, that means that our sample means will be normally distributed. So again, those results, very important to be familiar with those and used to the idea that once we start talking about distributions of means, the variance is reduced by a factor of n and the standard deviation by a factor of root n. And I have another little example here. This is actually a rectangular distribution, and I've chosen a population, so I've generated quite a lot of readings from a rectangular distribution, so theoretically every outcome should be equally possible. The mean is 50, the standard deviation 28.9. So you can see that this is heading towards a standard rectangle shape, and that's the population that we have. And remarkably, if we take out, and this is just a sample of size 25, so not quite up to the 30, but you can see that generating samples and plotting the sample means, and I've done that quite a lot of times, we have ended up very much with this bell-shaped curve. And again, the mean is still 50, the same as the original population. The standard deviation, though, is reduced from the original standard deviation by a factor of 5. So we originally had 28.9. Here our standard deviation is 5.8. So you can think about 28.9 divided by root 25, and that's pretty close to 5.8. And again, quite remarkable that we started with a rectangular distribution, but those sample means are indeed normally distributed, as the central limit theorem would tell us. And that concludes this video.